Hi everybody, in this video I just want to take you through Hess's Law. It's pretty simple. When you start reading the thermochemistry chapter in the OpenStax chemistry textbook, they have this weird kind of description of something called a state function. But all a state function is a path-independent function. What that means is that it does not depend on the path you take. So pretend like you're hiking up to the top of this mountain here, and you want to calculate your altitude gain. Now, it's only going to depend on the initial value that you start out with and the final value that you hike up to. It doesn't matter what the hiking path actually is. And it turns out that delta H, or the change in enthalpy, is also a state function. Basically, you just need to know that, therefore, Hess's rules work, and what I'm going to show you later in the next video is completely valid, okay? Now, let's remember and recall what is true of the change in enthalpy. So first of all, it's heat flow at constant pressure, so delta H is equal to Q, all right? If delta H is negative, remember, heat's released. It flows from the system or test tube to the surroundings. And if delta H is positive, heat is absorbed or flows from the surroundings, right? The room, the tabletop, your hand maybe, into the system, which could be the test tube or the beaker that you're holding. All right, so rule number one for the rules of enthalpy. So first of all, it depends on the moles of reactants. So if we have this combination reaction between carbon and oxygen to produce carbon dioxide gas, the delta H is negative 393.5. If we double the amount of all reactants and products, we get this balanced chemical equation with not the smallest whole number coefficients, but we have 2 carbon, 2 oxygen, 2 CO2. The delta H is just going to be double because we have twice as much material, okay? That's rule number one. Rule number two is that if you reverse a chemical reaction, you're going to have to change the sign of the delta H, but the value remains the same. So if we have carbon and oxygen combining to give us carbon dioxide, and the change in enthalpy for that process is negative 393.5, it means that it's going to release 393.5 kilojoules of energy. But if we flip that reaction around and we're going from carbon dioxide to produce carbon, which is a solid, plus oxygen, which is a gas, it's still going to require or involve the same amount of energy, but this time it's going to require the energy as an input. It's an endothermic reaction. So the delta H for this reverse process is positive 393.5 kilojoules. And this is the reason why when you see chemical reactions, oftentimes there's a plus or a minus in front of every single number that involves an energy unit, okay? To remind ourselves, okay, which way is the heat flowing out? Or which way is the heat flowing, all right, in general. So rule number three, this is technically the Hess's Law, is that the total change in enthalpy for a whole process is equal to the sum of each change in enthalpy for each of the parts. Okay, so pretend like this hiking trip to the mountain, it's done over 3 days. On the first day you hike up a couple thousand feet, the next day you hike up 6,000 feet, and on the final day you hike up another 12,000 feet, let's say. You know, you just add those altitude changes together to get your final altitude. And remember, the change in enthalpy is a state function too, so the same thing applies, all right? For example, let's say we have reaction one here, carbon plus oxygen go into carbon dioxide. That delta H is negative 393.5. And then reaction two, we have 2 water molecules being broken up into the elements hydrogen and oxygen. The delta H there is positive 483.6 kilojoules per mole. Now, let's say we wanted to sum these two reactions together, okay? So we're going to sum these two reactions, reaction one and reaction two. All right, now what you'll note is that there's an oxygen on the left of the reactant side of reaction one, and there's oxygen on the right, on the product side of reaction two. So if we were to add these two reactions up together, remember how in math you can add 2 equations together? Well, in chemistry you can add 2 equations together as well. All the left-hand side stuff goes on the left, and all the right-hand side stuff goes on the right, but we don't have oxygen, okay, in this balanced chemical equation. Now, what did we do for delta H? We just add them up. So negative 393.5, and we add a positive 483.6, and we get plus 90.1 kilojoules. All right, so maybe nobody has ever, this is a very common reaction, but you might be thinking, well, maybe nobody's ever done this reaction before. I'm just adding up two random reactions that I can think of that I have enthalpy data on. And yes, you can basically do that to see if a net process is going to be, exothermic, endothermic, or something like that. All right. Now, I'm not going to focus a whole lot on Hess's law. We're just going to go into the heat of formations and calculating delta H for different reactions. But just in case your professor for the class you are taking focuses on Hess laws, I just want to point out that it's kind of like solving a puzzle. You're going to be given 2 or 3 reactions, okay? And you need to decide how are you going to add those reactions to get the net reaction they're giving you in the word problem. Do you have to flip one? If you have to flip one, change the sign. Do you just add them together? If you add them together, you add the delta H's. If you have to multiply one of the equations by 3 or something, multiply the delta H by 3. Okay, and sometimes you have to multiply one by 1/2, flip, and then add, and there's all these different steps you might have to do. This is OpenStax Chapter 5, Problem 63, and we're asked to calculate the delta H for this process. Antimony plus 5/2 chlorine goes to produce antimony pentachloride, and so you're given reaction 1 and reaction 2 and the delta H's, and you have to kind of look carefully to see, do I need to flip one of these? Are the products and reactants on the correct sides? So we have antimony on the left for the first reaction, so that works out. And the second reaction, we have SbCl5 on the right. And you can see that, oh yeah, you just add these 2 reactions together because the SbCl3 term is going to cancel. And then 3/2 plus 1 is 5/2. So you get the answer there just by adding up your 2 delta H's, okay? Sometimes it's harder, but I've noticed that the textbook questions for the OpenStax are quite simple. Who knows what your professor might ask you? I don't focus on this in my class at all, but I just wanted to show you a problem. All right, thanks for watching. Please like, please consider subscribing to support my channel. Have a great day, everybody.